Hello. All right, here's our second example of finding eigenvalues and eigenvectors of a matrix. And spoiler alert, even though this matrix has real entries, 1, 2, -1, and 3, the eigenvalues are going to be complex. So that's a thing we have to deal with. All right, so let's find the determinant of A minus lambda I is the determinant of 1 minus lambda, 2, -1, 3 minus lambda is going to be that times that, 1 minus lambda times 3 minus lambda minus 2 times -1, and we're going to set that puppy to 0, right? These equal signs are all just how you compute it, and then that's what the business is. All right, so let's multiply this thing out. Instead of foiling it, I'm going to LOIF it. Last is lambda squared. Outer and inner is -3 lambda, negative lambda minus 3 lambda, so minus 4 lambda. And then the first of the LOIF is going to be 3. And then this is plus another 2 is 0. That's our characteristic equation, which is lambda squared minus 4 lambda plus 5 equals 0. All right. So actually, I'm a little bit tired. I keep trying this problem and I keep messing up. So I could use a characteristic. I could use the quadratic equation, but I'm going to complete the square for you. This is lambda squared plus 4 lambda plus 4, all plus 1 is 0. So that means this is just lambda plus 2, quantity squared plus 1 is 0. Or the characteristic equation is lambda plus 2 squared is minus 1, or lambda plus 2 is plus or minus I, right? If I square that, I get minus 1. So that means that lambda is minus 2 plus or minus I. So we get this thing has eigenvalues. Lambda 1 is negative. Oh, I screwed up. Oh, well. I screwed up. Hopefully it's not too bad to do. This is a minus 4 plus 4. That's lambda minus 2 squared. And that means it's lambda minus 2 is lambda minus 2 is plus or minus I. So lambda is 2 plus or minus I. So you can use quadratic formula if you want, but 2 plus I and lambda 2 is 2 minus I. All right. This is all good now, I hope. Okay, so that's step 1. Step 2. All right, so what is A minus lambda 1I? We're going to find the eigenvector for lambda 1. This is going to be 1 minus 2 plus I, 2, -1, 3 minus 2 plus I. Okay, so I take 1 minus lambda 1, 3 minus lambda 1. All right, so let's simplify this. 1 minus 2 is -1. And don't forget to distribute the minus sign here. And then I get a 2, and I get a minus 1. I get a 3 minus 2 is 1, and then another minus I. So right, so V1, which has, we'll call its components A, B, this satisfies -1 minus I, 2, -1, 1 minus I, AB equals 0, 0. Or that's two equations in the two unknowns A and B, minus 1 minus I all times A plus 2B is 0. That's the first equation. And then I have minus A plus 1 minus I B equals 0. That's the second equation. Now, usually two equations and two unknowns have a unique solution, but not now, because the determinant of this matrix is 0. It's got infinitely many solutions, including A, B equals 0, 0. So remember, V equals 0 isn't an eigenvector. So let's do this. All right, well, I'm going to call these equations 1 and 2. Okay, I think I like 2. 2 implies that A is 1 minus I times B, right? Bringing the A to the other side, okay? So if I let B equals 1, then A is 1 minus I, and V1 is 1 minus I, 1. Okay. Now, I'm going to trust that this equation is redundant, and I just use that one, okay? Or I could use equation 1 and trust that equation 2 is redundant. And equation 1 implies that, well, 2b is the negative of that times a, so it's 1 plus I times a, or b is 1 plus I over 2 times a. And I'll let a be 2, and then b is 1 plus I. So another natural choice is that v1 is 2, 1 plus I. Well, those are actually both good, okay? So unlike before, where everybody in the world could have a different eigenvector, I had 1, 0, you had 2, 0, she had 3, 0, etc. Here, they really don't, it's not so obvious that these are all the same. But they are, because these two equations are really only one equation plus another redundant equation. But another way of checking that is that, how could I do that? How could I check that? I don't know. I could say, this guy here, no, this, okay. So this guy here, I'm going to claim is, I can take the vector 1 minus I1 and multiply it by the scalar 1 plus I. Why did I multiply by that scalar 1 plus I? Because I wanted to make the bottom component 1 plus I, so the same as that. And what's the top component? 1 plus I times 1 minus I. That's of the form a plus b times a minus b. This is 1 squared minus I squared, when a is 1 and b is I. And this is 1 plus I. I squared, so let's go up here. This is equal to 1 minus negative 1, because I squared is negative 1 in 1 plus I. So this is equal to 2, 1 plus I. So indeed, this second form of the eigenvector is 1 plus I times the first form of the eigenvector. They're just scalar multiples of each other. And the upshot is, when you get those two equations for the unknowns A and B. You only have to look at one of them, solve for that, and you're done. You just say, here, V1, take your choice. I kind of like this one because the numbers are smaller. 1 minus I, 1. Okay? So what I'm saying here, the upshot of all that is, when you're doing it for yourself, this is going to work. This is all you have to do. You might want to check your work, but another thing that you can sometimes do is going to be important is this can be written as 1, 1 plus I times negative 1, 0. Okay? It's just sort of like we sometimes write a complex number as, say, 3 plus I times 5. This matrix plus I times another matrix is that matrix with complex entries. Okay, so that was a lot of work, but the good news, so the bad news is you're dealing with complex numbers. The good news is V2 is a piece of cake. Since lambda 2 is the complex conjugate of lambda 1, V2 is the complex conjugate of V1. It's going to just be 1 plus I, 1. Okay, all the equations you get to solve for V2 are just like the equations you get to solve for V1, except you replaced I by negative I. So in the solutions, you can get the solutions by replacing I by negative I. And 1 minus negative I is 1 plus I, right? Okay. All right. So in the next video, I'll think about what happens if we try to find the eigenvalues of this matrix here that has an arbitrary constant in it. All right, bye.